In the previous lectures, we've talked about regression examples where you have a quantitative outcome and one covariate of interest, whether that's a factor variable or a continuous variable that you're trying to relate to the outcome. In this lecture, we're going to talk about multiple regression, which focuses on using multiple covariates in your model. And we're still going to use the same sort of least squares approach for fitting the model, and then the central limit theorem for providing sort of inferential approach or machinery for providing inferences. And we're going to pay careful attention to how we interpret the coefficients that we get from multiple regression because it can be a little bit tricky, particularly if you have sort of interaction terms that you're dealing with. So the data that we're going to be dealing with are going to be focusing on this Millennium Development Goal 1, which is to eradicate extreme poverty and hunger. You can read a little bit more about the Millennium Goals here at this website that I've linked to. The data set that we're going to be using though is actually from the World Health Organization, and here's the link to that data set. I'm going to first download the file. Here I'm downloading it with download.file, and sorry, the link got cut off, but you can see it on the previous slide. And then I'm going to read the data set into a data set called hunger, and I'm going to actually eliminate, there's a bit of a tidy data problem in this data set in the sense that they have the values for the males and the females, and then they average those values into both sexes. And so I'm going to actually eliminate those values and just use the numbers that I calculate for males and females. And so what we get actually is a value of numeric, which is basically the numeric variable here is the percent of children aged under 5 that are underweight, and then we also have the sex of the children, and we have the country that they're from, and the WHO region that they're, the WHO being the World Health Organization region that they come from, and the year that we actually calculated the percentage of underweight children. And so the first thing that you can do is you could plot, say, the time that the measurement was taken versus the percentage of children that are hungry. So remember, this numeric variable is just the percent that are hungry. And so we get a scatter plot that looks something like this. And so we could fit a linear model where we relate the percent that are hungry to the year. And so if we had to interpret this model, we'd say that B0 is the percent of children that were hungry at year 0, where year 0 is 2,000 years ago, and B1 is the decrease in percent hungry per year every year according to this linear decrease. And EI, again, measures everything that we didn't think to include in the model or measure. So we can actually add the line that comes from the linear model. I hope you can see it. It's in light gray here. You can kind of see it traverses from left to right there. That's the best fit line to these data relating hunger percent to year. And then the next thing that you could imagine doing is breaking that down by different other variables. And so the first one to think about would be, say, the male-female difference in hunger. And so in this plot, all the males are colored in black and all the females are colored in red. And so we can see the percent hungry versus the year. And you can see it doesn't seem like, at least from this first glance of the plot, that there's too much different about those distributions. So what we could do is we could actually fit a separate line to each one. We could fit a separate line to the females and to the males, and so the females have their own intercept term and their own slope and their own errors, and the males similarly have their own intercept, slope, and errors. And we could actually fit those lines in R using the LM command, and so we've done that just by subsetting to the males on both the sort of outcome variable and the covariate variables, and then doing the same thing with females here. And we can then make the plot that we did before, which is just year versus hunger, and we can overlay on top of that the lines that we actually estimate for the males and females. And so you can see, once you actually do that, you can see that the line for females it looks like about the same slope as the line for males, but there's sort of a difference. The female girl children tend to be slightly less hungry than boy children, sort of across a long spectrum of time. So one thing that we could do with linear regression is that we could actually make this a little bit easier to fit these lines, and if we wanted to allow them to only have the same slope so that we only get one slope for both lines, we could fit a model like this where we have an intercept term plus a term times this dummy or indicator variable that the sex is equal to male, plus another term that is the term for the percent change in hungry for either males or females in a single year. So this is just like sort of the line that we had before, the equation for the line that we had before, but now we've included more than one term in the model. And so that affects how we interpret the variables that we get out. It also affects how we fit the model a little bit, and then it affects how you interpret what the results that you get are. So if we have these two lines with the same slope, we fit them by fitting that model from the previous page. And so what you do is you say, okay, we're going to take the percent hungry as the outcome variable, and then the covariates are going to be the year and the sex. And if we have more than one, we're just going to use this notation in R. You say tilde, the covariates that you want to include in the model, separated by plus signs. And so now we can plot again year versus the percent hungry, and we can add on top of that now a linear model fit for each of the two categories, so the boys and the girls separately. And you can see it looks a lot like the plot I showed you before because the slopes are the exact same in this case. They were very close to the same previously, and they're a little bit off in terms of their intercept. That's the main difference in the two cases. So the other thing that we can do is we could actually allow each line to have its own slope in this linear modeling framework. So again, we have the percent hungry is equal to some baseline. In this case, that's the percent hungry at year 0 for just females. And the reason why it's just females is because we've also included a term here that is equal to 1 if the sex is male. So the percent hungry at year 0 for males is just B0 plus B1. And then we also have a term here that's equal to the percent change in hunger for just the females in 1 year. And then if we want to say the percent change in males, well now if you're male, you have this term B2 times Y, but if you're male, this term here, this indicator or dummy variable is also equal to 1. So you actually get a B2 plus a B3 times Y. So B2 plus B3 is the change in percent hungry for males in 1 year. And again, EI is everything that we didn't measure. So if we plot those lines, they look remarkably similar to the other lines, and I think that's because in this particular case, the slope is almost identical between in the two cases. That's not always true, especially when you're including an interaction term. You might get lines that have very different values for the slope because you're allowing the linear model to estimate both of those values. So then what we can do is we can actually look at the summary of the model fit where we include both terms and interaction term. And so when we include an interaction term, we can actually go down here and look at that. This is the interaction. This is how R indicates an interaction term with this colon. So it's saying here's the indicator that you're a male, and this is your year variable, and the coefficient is minus 0.028, which is substantially smaller than any of the other estimates. So that's probably why the slopes aren't too different between the males and the females, because this number here, this is the estimate of B3, is the difference between the slopes for the males and the females. So again, it's not very significant statistically, but it's also just so small a value that you actually think that they're almost nearly identical slopes. To include quantitative terms in interactions in multiple regression models, but the interpretation gets a little bit tricky, so you have to be a little bit careful. So for example, suppose that we had an income variable that was measured in dollars, and we're fitting a multiple regression like this where we have a term for income, a term for year, and an interaction between income and year. Then B0 becomes the percent hungry at year 0 for children whose parents have no income. So imagine if income is equal to 0 and year is equal to 0, these three terms all go away, and we end up with just the B0 term. So that's the average percent hungry at year 0 for parents with no income. B1 becomes the change in percent hungry for each dollar of income in year 0, because if year 0 is equal to 0, this term and this term go away, and we just get the change in income of $1 will lead to a change of B1 in percent hungry. B2 is the change in percent hungry in 1 year for children whose parents have no income. So if income is equal to 0, this term and this term goes away, and for each increased year we get an increase of B2 in percent hungry. And then B3 is the interaction term, and it's the increased change in percent hungry by year for each dollar of income. So this is a sort of a very tricky one to interpret. So you can imagine if you had an income of $10,000, then the change in percent hungry in 1 year will be the change due to this term here, B2, plus you have an income of 10,000 times the year times this term, B3. So you get a change of B2 plus 10,000 times B3. So you can imagine as income goes up, the change actually changes. So this is a bit of a tricky thing to interpret and hard to keep in mind if you have interactions with continuous variables. And finally, E measures everything that we didn't measure or include in our model. So the key take-home message here is just that you can do this, but lots of care and caution is needed, and you have to be very careful about putting together the interpretation of those coefficients when you have interactions with continuous variables.